29.35. A rectangular circuit is moved at a constant velocity of 3 meters per second into, through, and then out of a uniform 1.25 Tesla magnetic field, as shown here. The magnetic field region is considerably wider than 50 centimeters. Find the magnitude and direction, clockwise or counterclockwise, of the current induced in the circuit as it is A, going into the field, B, totally within the field, and C, moving out of the field. Sketch a graph of the current in this circuit as a function of time, including the preceding three cases. Okay, so step one, let's look at moving into the field. So when we're going into the field, our induced EMF minus d by dt flux. The flux of this guy as he's moving into the field is going to be B times our area. So as we're moving into the field, the length here, we're going to call this one L and this one W. The length is going to stay the same, and the width that's exposed to the field is going to depend on the velocity, just like everything else. So the width exposed to the field is going to be velocity times time. So our time derivative of that is our BLV. Like always, we're going to ignore our minus sign for now because I want to use the right-hand rule to figure out, or pictures to figure out which way it's going, which is all the minus sign does. So our induced EMF is BLV, and from Ohm's law, V equals IR. Our current is going to be B over R. And our voltage is our induced EMF, so that's our BL velocity over R. So our B field is 1.25 Tesla. The length is 0.75 meters or 75 centimeters. And our velocity is 3 meters per second over our resistance, which is 12.5 ohms. So the current that gets induced, if we stuff that into our handy dandy calculator, 1.25 times 0.75 times 3 divided by 12.5. It's going to be 0.225 amps. Alright, now exiting the field, it's going to be the exact same magnitude of current, because the area is going to be changing by the same amount, V times T, as it comes out as it does going in. So the magnitude of the induced current going in and coming out is going to be the same. They're just going to be in different directions, probably. We'll check that in a minute. When we're actually inside the field, so inside, when we're actually moving through the field, the flux through my square is staying the same. My flux isn't changing. I still have the same amount of field in my square as I move it along. The area that is exposed to the field is constant as I go through the field. It's only coming in and coming out that flux is changing. So inside, my induced current is going to be 0 because the flux isn't changing. So we'll just say d by dt of my flux is equal to 0. Okay? So going into the field, we're starting off with only, that is not the right direction, with only a couple little magnetic fields. And then as we're going further in, we're picking up some more. So Lenz's law likes to keep things the way they are. So I'm increasing the flux. So I want to oppose that change. So I'm going to induce a field that's going to oppose this increase in flux. So that's into the page. My field is going to induce a current going this way. as it moves into the field. Now on the way out, I'm starting with a full flux, and then as I'm pulling out of the field, I'm getting less. So in order to counteract that and go back to the way I was, I need to induce some extra out of the pages. So if I induce them out of the pages, my current is going to be going that way as I move out. So if I plot this, let's say positive is clockwise and negative is counterclockwise. So as I'm moving into the field, my current is nice and constant at 0.225 amps. Once I'm fully inside the field, my current is 0. And then as I'm leaving the field, my current is 0.225 amps in the other direction. And then once that's fully out of the field, it goes back to 0.